Okay, let's get started. Today we are going to talk about Gaussian process. We continue our discussion from last time, and next class would be our last class, and we're going to have a guest speaker. After that, we are not going to have any class, and then we're going to see each other again when we are talking about your projects. I think TAs have already sent enough information about the structure. We are going to have, I think, 6 of the project to be presented in person, and the rest will be posters. I think if not enough detail is posted, we are going to work on it and give you the exact schedule. Any question? Okay. So we talked about Gaussian process last time. We mentioned that many of the classical problems in machine learning, such as regression and classification, boils down to estimating a function. And the goal of Gaussian process is basically making it non-parametric. We gave this example that, let's say, if you start from this data, which is the number of airline passengers since 1949, and we want to predict the number of the airline passengers, and we said that at the end boils down to estimating a function that estimates the behavior of the market. And the key idea behind all of this is how complex that function would be. If it is over complex, it may result to overfitting the data but not predicting the future correctly. If it is too simple, may get the general trend correct but not the fluctuations in the detail. And we mentioned that the general idea of non-parametric estimation is started basically with parametric model. So let's say that if we have a simple parametric model, that there's a theta that is shared at the end, if our goal is just prediction, what if you just integrate out all of this parameter and focus on this joint distribution of the training, the label of the training data and the label of the test data given the covariates. So we mentioned that the goal of this Gaussian process is just go there and directly model this probability distribution without having exact mentioning of the data. We start with very simple example. We said that what if, let's say, start with linear regression. We have input a vector of x and then a feature space phi x. And we are, just for simplicity, we assume that, let's assume the noiseless prediction for y. Then the linear prediction become inner product between some parameters and the feature vector to predict y, assuming that w is coming from some Gaussian distribution. We mentioned that like we can integrate w out, and then we have a form of the similarities between y's. So that depends depending on how we can choose phi. So it can be linear function, it can be quadratic function, it can be any complicated function. All of them at the end boils down to some sort of a smoothness between input data x and prediction y. If two x's are close to each other, you do expect, based on the smoothness, their y's to be similar to each other. That's basically the general idea of this non-parametric model, that have this smoothness in between. So for example, if these black dots are representing my training data, if my test data comes in between, I do expect my prediction to be in between these values. But if it gets further away, I have a higher variance on predicting what the value of the y would be. So here, these are my tests, and the black dot represents my training. Right? So this is basically the general idea. Anybody has a question about the general idea of non-parametric approach? Yes.
In the last slide, since you condition on x and x star,
yes.
Do you need to condition on y? Because y is the data you condition on the data and you predict the only.
That's a good question. So I have to say two things. First of all, here we are not interested. We are interested in only prediction. So hopefully you see that there is no reason to go and directly estimate x's, right? So we don't care about, so if we only care about predicting y, why should I spend my computational resource on estimating x's? So this is in a so-called discriminative setting. That's one. So now you mentioned that, well, if y star is my test data and y is the space of all of my training, what I'm actually interested in, my predictive likelihood. And so y star given all of the data and given all of the training, this training, and x star, which is my test. Yes, you're right. You're right. But you can see that you can estimate. So the form having some form of smoothness on this impose some form of smoothness on this one, because if I want to estimate that guy, estimate that, I can write it as a join, which is this, by some normalizer, right? Which my normalizer become y given everything, right? So does it make sense? So you assume some form of a smoothness on this joint distribution of the y's, conditional y's, and then when you want to predict at the test time, you say that this is the joint likelihood on the nominator and the marginal likelihood on the denominator. The same way that we always do. Is the setup clear? If it is not, I'm going to build on the top of that. Okay. So we said that, okay, let's continue with this example. So let's say that we have a linear regression, or phi is going to be just x. Well, okay, sorry. So my y is going to be some linear function of the phi's. Right. Okay, so the joint distribution would be the result of integrating W out, because I'm imposing some sort of probability distribution on W. There is no W here. I have to integrate that out. So if I write it as in that form, remember that this is because I'm conditioned on x, this is constant, this is Gaussian, this is going to be Gaussian. So if I write the joint distribution, at the end, the joint distribution is going to have a form that looks like this. That is going to be, if I write the joint distribution of all of these y's, it's going to be a normal distribution with a covariance that is outer product of all of these features. This is what we worked out last time. So we mentioned that, well, at the end of the day, we are interested in modeling this joint distribution. And all it shows up here is that it's going to show up as k, which is the inner product of the features feature vector. What if we just throw out explicitly modeling phi and going and saying that, well, element of all of these k's look like that the inner product of some features. Do I need to have the exact form of phi? Because all I need to care is having some sort of like a kernel, some sort of a matrix that is as big as number of samples by number of samples. I don't need to have the phi's exactly. So that was the idea behind having this covariance function that I'm going to discuss today in more detail. So this is the recap from the last time. We introduced a few standard covariance functions. So we mentioned that the whole idea of this covariance function that basically model this. So if I have two data set, xy and x2, is going to model phi x1, phi x2. Okay, this is my covariance function. So there are several examples, so several very useful, very common examples. Of course, a very simple example of that would be linear function. So in that case, if I assume that I don't do any featureization, I just use the same x. No feature extraction, just the phi x is going to be x. So in that sense, my k is going to be set of all linear predictors. I can use what would happen if instead of going directly for different forms of phi, I say that all I need from this k is to have to act like an inner product. So one of the ways to do that is say that, like, what is inner product exactly? What is this similar? It's more like similarities between data. If two data are similar, it should be higher. If two data are less similar, it should be lower, roughly speaking. We're going to make it more formal, but that's roughly speaking. One way of doing that is to use square exponential that you guys probably have seen it as RBF kernel. So this is basically RBF kernel. The question is that what kind of phi produced this RBF kernel? So the answer to that is that was basically one of the reasons behind why we went there to directly model K instead of going and designing phi. If the algorithm that we are interested in just have to impose some sort of similarities between them, I don't need to have a phi. My phi can be infinite dimensional. So all I need to compute at the end is this inner product. So I don't need to do that. And it turned out that, for example, for RBF kernel or for Matten function, Matten kernel, the form of the actual underlying phi that induce these kind of kernel are infinite dimensional. So I'm going to give you a little bit more intuition on this. What do I mean by infinite dimensional? You can think of it, like, vaguely speaking, of a function as an infinite dimensional object. So you can think of a vector as a finite dimension and a function as infinite dimension, because there's so much variation, you cannot put it in a finite space. So I'm going to give you examples of how these guys are going to behave in a function space. So this is the kernel space that induces some function phis, and I'm going to show you some examples. But before showing you that, you can see that some of those have a specific form. For example, if you see a square exponential, you see that it always shows up that the form of k, x, xy, shows up as some sort of like a function of x minus x hat. Which means that if I shift x and x prime by a vector of d, this is not going to change my kernel. So this is why it's called stationary. Because if you think of it as a signal, and this is the origin, it doesn't matter you compute the similarities between this x and this x, if the distance between them is d, here, or compute the distance between them here. So let's assume that the distance between them is both d. This is x1, this is x2, this is x3, this is x4. The distance between them is always d, so the amount of similarities between them is always constant. If the form of kernel looks like this, that it always shows up as a function that there is always xl minus xl prime, so this is the lth element of the x, shows up in a function that's called stationary. So let's go and take a look at the examples of a few of these functions and see what kind of phi function they produce. So I'm going to for the people in the section B, I'm going to post this IPython notebook online. I guess because of our video setup, you might not be able to see that now. Ooh, wow, that's huge. Is it better? Okay, good. All right, so let's start with some examples. What would happen if my kernel is so-called RBF kernel, or squared exponential kernel? So the form of that is going to look like some function x minus x prime, the norm of x minus x prime, with some normalization to the exponent. If x and x prime are very similar to each other, or like almost close, almost identical, it's going to produce 1, like very, very similar. And as they get further and further away from each other, this kernel goes down. So let's make some of these and say, take a look to see what kind of function in a space that are going to be this kind of kernel induce. So let me draw a couple of samples from this function. So as you see, oops. Didn't move this guy around too much.
I think it should be n underscore samples.
Yeah. It's probably, let's see, yeah. But this is what happens when you want to make a demo. Okay, so here is some examples from this function. So you can think of this kernel as a function that's induced by this. So I told you these functions are like more like infinite dimensional objects, and K is more like a similarities between them. If you choose, for example, RBF kernel, the function is going to look like these smooth functions. So every time that I draw a sample from it, it's going to be different functions. So let me make this maybe lower so that you can see few examples. See that every time it's going to be very smooth function, but that's it. So that's basically the behavior of that. So what would happen if I change, for example, the kernel from Gaussian process to, let's say, Matern kernel? So Matern function, if you remember, looks like this, that there is some sort of like a distance between objects minus the Bessel function of the second order of the distance between them. So let's see what kind of behavior that is going to induce. So if I draw some some samples from that, it's going to look like something which is less smooth than Gaussian, than RBF kernel. So why am I showing you this? You can think of the RBF similarity matrix as sort of like a space that implicitly specifies the behavior of the function that's living in that space. For example, if you compare the behavior of this with this, you see that in the Matern kernel, the functions are more jagged, right? It's less smooth. And with changing the parameter of the Bessel function, I can make them like second order. I can control the number of the derivative that this function has. So instead of specifying the function explicitly, I can say that roughly this should, my feature function should look like this. Should be all the space of, let's say, periodic, all linear function, all quadratic function, all polynomial, instead of specifying specifically parameterizing it. And the beauty of that is that although for simple stuff like linear, quadratic, polynomial, it's a finite dimension. You can specify the coefficient of the polynomial and be done with it. For some of the functions such as space of all of this smooth function with infinite infinite gradient, you cannot specify it with a finite number of functions. While if your algorithm, for example, in this case Gaussian process, all it needs is to have is like inner product. You don't need to specify directly. You can say that this is this entire space, vaguely speaking. So let me give you another example. This is another function that is another kernel that produces a bunch of periodic function for you. So I'm going to show you an example that when it will be useful. You see that every time that I draw examples from this, it's is going to produce some periodic function. Oops. Is the general idea clear? Yes?
Is there some term in like a posterior that you can interpret for the periodicity if you use this type of?
So far I'm just like drawing samples from prior. I haven't talked about the posterior. But that's a good question. So your K space says that, so basically the idea here is this. I'm presuming that the space of my prediction, the function I would like to predict, are a space of all infinitely differentiable functions. So your posterior is going to still live in the same space, if that's your question. So if K is the space of all of this infinitely dimensional space, using vanilla version of the Gaussian process, your posterior is going to live in the same space. But based on the data, the form of this function is going to be different. So right now, I'm just drawing sample from the prior, and you see that it's just, okay, so this one is just going to look like some sort of a periodic function. But by putting more data around it, so let's say that if I say that this should be, so at the location, let's say -3, it should be, let's say 3. So it should be all of this periodic function that on the -3 produce 2. And then I can confine this space.
I guess, sorry.
Now go ahead.
Does the choice of covariance determine a specific kernel space,
Yes,
and does your posterior live in the same space?
That's right.
And then in that case, do you get any outputs from the posterior, I mean, once we get to that you can interpret in the same terms as the prior? You can interpret the same term in terms of space. So we can say that if the covariance function producing, let's say, set of all differentiable periodic functions, right? So your posterior is going to be living in the same space subject to the data. So it means that, okay, so you can think of it as an interpolator, right? So I'm just going to say that I want to, on a coordinate 3, I'm going to have 5. On a coordinate 0, I'm going to have 6. So find me all of these periodic functions that produce this value on that location. Okay, so in that case, anything that you put in is just tuning parameters, and the posterior will have the same tuning parameters, so it's not like you're fitting any...
I'm not parameterizing function at all, right?
You have no tuning parameters?
No. Well, I do have a tuning parameter of my general space. Okay, for example, if I change it, I think I have some examples here that I can show you that. For example, in the RDF kernel, in the square exponential kernel, you saw some parameter, right? Where is it? You have this parameter, right? These basically specify the behavior of your space. If I make it small, it has one behavior. If I make it big, it has another behavior, right? So that implicitly says that this is the behavior of my space. So during your learning process, you can find the optimal lambdas or optimal parameters. So let me show you some examples of that. I made this a couple of days ago, and sorry that sometimes it may have hiccups in demo. So let me generate some data. So this, let's say that this is my real underlying function that I want to predict, right? This is my data. This is mixture of, I guess I made the sinus and sinus square, right? This is my, and some quadratic, right? It has some general trend and some sinusoid behavior to it. This is my underlying true function, right? So this is my underlying true function, and I'm going to generate some data from it. What happened to my data? Okay, so this is my underlying function. I'm going to draw some sample from it with some noise, right? So this is my true function, right? And this is the samples that I have given. So for example, let's say that, how can I say, it's like this is your one-dimensional domain, and let's say that this is some parameter that you're measuring, I don't know, temperature. I mean, this is very funny behavior of temperature, but it's something, right? So you have a measurement or sensor here, with some noise, right? You don't have access to this blue. You only have access to this red, because that's your data, right? Now, I want to estimate the behavior of this, for example, for this location that I don't have access to it. How can I do that? So this is basically the behavior. I'm going to show you some examples of that. Is the setup clear? The blue, my underlying function. Red is my sensors. So let's go and do some prediction. So let's start, for example, with SE kernel, square exponential kernel. So I'm going to make a kernel between my training data, XS. My training data would be these locations. And I won't go through all the detail of that, but basically, to draw a sample from any Gaussian function, all you need to do is to generate samples from Gaussian with covariance of I, and multiply with the square root of your covariance function, which can be viewed as a Cholesky factorization, but that's not important. So let's say what do I miss? Sorry, guys. I think last night I moved some of the blocks, so this is what happened. You moved some of the blocks. Okay. So you see that this is the behavior of my function. So this was my training data, right? And wherever I have a training data, I have a lower variance, right? But as I go further away from my point, the variance increases because I haven't observed anything. So I have big variance about the location that I haven't observed. So, okay, so I do this training. So remember how my prior look like. So my prior on SE is going to be a bunch of smooth functions that are infinitely differentiable. Now I'm confining them, I'm limiting them with some observation on these locations. So what would happen if I draw a sample from posterior? So this is the form of my posterior. The thick blue line is my true values, and the different colors represent the sampling from posterior. And as you see that all of them roughly have to meet in the location that I have observation. In the location that I don't have observation, they have a freedom to wiggle. So let me draw another sample from it.
So at the point where you have a prior data point, you have zero variance, but that in some sense
Have zero variance? Where do we have
zero posterior variance, right? Because
I mean, it's not exactly zero posterior variance because if the true underlying function does not live in a space that you parameterize it, it's going to be some variance, right? Because so let's say that this is space of all of, so let's say that this is quadratic just for simplicity. The true is quadratic. And there's no quadratic function in my space. I won't be able to capture it, right? So my function is trying to get close to that. So there is some variance, but it's small. Yes, please continue.
yeah, so is it possible in order to tune that posterior variance for the points that you have in order to make it more flexible and not want to approximate the training data?
So you mean, so all parameters that I have is parameter of my kernel, right? Because I mean, I'm integrating all those W. Remember that W? And that's integrated out. That's not my degrees of freedom because that's marginalized out. All of the parameter I have is whatever parameter is left in my kernel. So basically by changing that, I'm changing the space of my function. I can make them smaller, I can make them bigger so that it can meet those area. But hopefully this figure is clear to you, what this figure represents. Is it clear? Okay. So what would happen, for example, if I sample from Matern kernel? You see that, for example, this function is better represented by Matern kernel than Gaussian process. Because as you see, the envelope of, you can think of it as an envelope, right? You can think of this blue as an envelope of all of these functions, because this shows, I guess, like I'm showing 3 standard deviation of the function that can live in between. So you can think of it as like, there is no function that goes beyond this, or the chance of that is very low. So you can see that all of this function lives within this envelope. And this envelope is slightly smaller than this envelope, right? This envelope was very violent, right? So this envelope is smaller, and when I sample from posterior, they are following the true distribution much more closely. So the choice of the kernel matters, to answer your question. So let me draw another sample from it. See that this blue, the thick blues represent the true, and different colors are just different samples from the posterior. So what would happen if I choose a bad kernel? For example, in this case, this is not periodic. If I choose, for example, a space of all periodic function, is not going to fit well to this. So let's see the behavior of that for that function. So you see that this is not fitting it very well. So it says that, well, the best periodic function that I can fit to this data is this. I cannot do better than that. Right? So it's not, yes?
Does that periodic function have to be constant mean?
Well, you can I'm going to show you some example in the following that you can combine different kind of kernel, but here I'm just showing you a very simple example that if I choose a bad kernel that says that space of all periodic differentiable function, right? This is not, if your data is not periodic, it's not going to fit well. And so you can see that already here, that it says that it's going to hallucinate some sort of periodicity in the data. So it says that to me, it looks like that there is some something happening here and something happening here. I'm going to ignore the rest. And this is the space of periodic function that I can choose. Maybe by changing the parameter, you can change the frequency of this, but that's it. You can't really, because the space that you're searching within is all periodic, and it's not periodic, you have no chance. Okay, so that's basically the general idea. So let me go back to this again. So hopefully you can see that the K represents the space of all this function implicitly. So, and this phi function can be, is your space of features, but you don't have to have access to this directly. It's sort of like implicit feature space that you have. So one question would be, how can I come up with a new covariance function? So it seems that that's very important, what kind of covariance function we choose. Actually, you have very little limitation on this covariance function. All you need to do is that you have to make sure that your function is positive semi-definite, which means that, remember, if the matrix is positive semi-definite, it's positive semi-definite if for any x transpose x is non-negative. So how can I extend it to a function? The extension to the function would be if I take a, so you can think of this as an integration. So it's like there is a sum involved in matrix vector product. You can replace it with the integration, and basically you can write it as like fx k x transpose x prime, and integrating over that should be non-negative. If you come up with a function that satisfies this property, here you go, you have your own space. And there's a theorem that there's a one-to-one correspondence between K being covariance of the Gaussian process, and K being symmetric and positive semi-definite. So that's all you need to do is to come up with a function that has this property. So what is the connection between kernel matrix and covariance function? So basically the covariance, the kernel matrix, which is finite dimensional, is going to be number of samples by number of samples. Is you can view it as sort of like an inner product between these phi. So remember that I mentioned that this phi is this infinite dimensional feature space that you don't really know how exactly it looks like, but all you need to do is to be able to compute this inner product between them. So the kernel matrix is a matrix that's filled up with this inner product. So ith element of that is basically filled up with this kernel matrix. And this is the object that we are dealing with in reality when we are looking with Gaussian process. So this K matrix is number of samples by number of samples. Is it clear how we go from K covariance function to kernel matrix? Yes?
Are you referring to phi as the function?
Phi is a function, exactly.
Kernel, kernel function, is that what it's also called sometimes? Or?
So this phi is your feature function, right? This is like, it gets the input phi and produce something that's potentially infinite dimensional. Doesn't have to be infinite dimensional. For example, if I choose K to be linear kernel, this is equivalent of choosing phi, which always produce X. You give X, produce X. So it's like it's very simplest function. So the K, the kernel matrix, the covariance matrix between x1 and x2 is going to be space of all of these linear functions. So, but you don't need to have access to phi. All you need to have is to be able to compute this inner product, and this inner product is computed by K. So you can fill in this kernel matrix by plugging in different data set and filling that up. Is the setup clear? So what would be the phi? The phi would be these infinite dimensional phi. We don't deal with phi, I have to say that, but I'm just showing you to give an intuition that what is the connection between this phi and kernel matrix. So the phi, intuitively speaking, is you can think of it as a space of all of these functions. So you have as many samples that you have in your data set, and you have an infinite dimensional object that fills this phi. So more mathematically speaking, you can think of phi as an operator that maps a data set and produces a function for you. So, and the kernel matrix is inner product between that. So if in this case, a little bit like a, vaguely speaking, is going to be R, let's say, infinite dimensional by n. So my phi transpose by phi is going to be n by n. But as I told you, in our Gaussian process, the object that we are dealing with is just K. We never deal with phi. But it's good to have this intuition behind in your head. So this phi function that I told you is like an operator that maps your feature space, which is, let's say, I don't know, d-dimensional, it has to be d-dimensional, to a space of all of this function, So for example, if I chose kx x prime to be something like, if I define it as that kernel function that I showed you earlier as a space of all periodic, f is going to be space of all of these periodic functions. So you specify kernel covariance matrix, and that will specify your phi. So you don't have to go and directly specify your feature vector. Clear? Okay. So now that we have talked about the covariance function, let's start and introduce Gaussian process formally. So the Gaussian process can be viewed as a prior over function. That these functions are specified with your covariance matrix, covariance function. So at the end of the day, there are some sort of smoothness specified by covariance function. But the beauty of that is that because all you care about is prediction, and in all of your prediction, this kernel matrix is going to show up. You don't have to specify your space of your function exactly and explicitly. So the Gaussian process, formally speaking, can be viewed as a collection of random variables that any finite specification of that has a Gaussian distribution. So give you an example, to give you a solid representation, if I have a Gaussian process with mean k and the covariance function phi, every time that I draw from it, it's going to produce a function for me, right? the example that I showed you earlier. But if I go and evaluate it for different features, this is going to be finite n-dimensional representation. That this finite n-dimensional representation has a multivariate Gaussian distribution. That this multivariate Gaussian distribution, this is going to be kernel matrix. Remember, this was covariance function. But this is n by n. And this is another function. This is like a finite dimensional. This is going to be n by 1. And again. And this is basically the setup. So the Gaussian process, as an infinite dimensional object, every draw from that is going to be function. But if you go and evaluate in each of these locations, this finite dimensional representation is multivariate Gaussian. Is this clear? You should stop me if it's not clear now. Okay. So let me give you more example. Hopefully, I can give you some example here. So what we are assuming here is that, remember that I was drawing sample from prior here. Remember that? I was drawing sample from prior. So every draw from my prior was a function, right? But the actual object that I'm using is basically these samples that are drawn from this, like, let's say that this 10-dimensional, this 20-dimensional space. If I go and substitute these 20 coordinates into my function, this 20-dimensional object is multivariate Gaussian with 20 dimensions. Make sense? So if I have more samples, I'm going to increase the dimensionality of that multidimensional Gaussian. But my underlying space is infinite dimensional. Because the space of all of this function is specified implicitly by my covariance function. Okay. So what is the nice thing about this Gaussian process? The beauty of this Gaussian process is that it's relatively easy to do inference on it. For example, for things such as regression is basically closed form. So it brings specifying an infinite dimensional object, which is very appealing. You don't have to have infinitely many parameters. But still, the inference on this space is quite computationally approachable. So give you an example. So let's say that we want to do regression. So if I want to do regression, I have set of training data with some input features and some value that I would like to predict. So X is my space of all input features, a vector of features, and Y is the output. Now, I can go and say that, well, my covariance function is a function. I don't know how it looks like. I can roughly specify it. For example, if I say that SE is going to be all of the space of all of these infinitely differentiable function. Let me go back and construct a vector that basically these vectors are evaluation of each of these input space for each of these coordinates. So remember, my x is first input, second input, and so on and so forth with xn input. What would happen if I go and evaluate those for this distribution? So f is going to be n-dimensional object. It's because I have n samples, right? Remember, in a Gaussian process, we said that the space of Gaussian, so draw from the Gaussian process is going to be infinite dimensional object, but this is a final dimensional representation. So this is going to be Gaussian, multivariate Gaussian with n dimension. What would happen if I given the test data? So my test data is going to be x star. That is going to be x star 1, x star 2, and so on and so forth. How the joint distribution of my function is going to change after input of the test data. So this would be the space of all of these tests. So you can think of this as a concatenation of training and testing. Remember, in a non-parametric model, we will go, instead of parameterizing the space explicitly, we went there and then go after parameterizing the joint distribution, right? So if I concatenate one Gaussian with another Gaussian, the result is still going to be Gaussian, right? So this is my prior, the space of all of these functions that are coming from my prior, and the result is going to be zero mean with the covariance between training data, covariance between training and the test data, and covariance between test and test data. This is my prior, because this is, I'm assuming that it's coming from Gaussian distribution, Gaussian process. So if I want to compute the posterior, which is basically, I want to say that what is the posterior probability of f and f star given the input, is going to be proportional to my prior multiplied by likelihood. So what do I have in the likelihood? It's basically my noise model, right? So if my noise is, for example, is a variance with a spherical variance with covariance with a variance of sigma squared, this is another Gaussian distribution, right? This is another Gaussian distribution with the mean, which is the mean of my training data, and with a variance which is sigma I, right? Because I'm assuming that my real model is fx plus some epsilon, and this epsilon is, right? The nice thing about that is that because this is Gaussian, I can absorb them together. And all it shows up is that the covariance of this is going to show up as a kind of like a regularizer into this element of state. And what is nice about it is that this is my observed values, this is my test data, and I know all kinds of operation in a multivariate Gaussian. I can easily compute the conditional. You remember that you guys have seen that if I have x and y as a normal distribution, as a multivariate normal distribution with mu and k, let's say mu and sigma, you can easily compute px conditional y. You have seen that probably in homework 0. Well, here we go. All you need to do is to compute the mean of distribution, that all it shows up is the kernel between training data and training and the test data, and the Shor complement. So at least for the regression case with the noise, the posterior has an easy closed form. Is this clear? That y we get to y posterior has a simple closed form?
very similar to kernel regression.
Well, this is basically it is basically kernel regression. It's just like I'm saying that to you from a Bayesian point of view. So what I'm saying here is that at the end of the day, for the test data, what we are interested in computing the posterior. Given all of my training and parameters, these are my parameters, right? These are my parameters that I have to learn. I'm assuming that I've already learned, like this, I fixed it. I'm interested in computing posterior. So my posterior still is going to be Gaussian, right? Because my joint distribution is Gaussian, my condition is also Gaussian. So but it has very simple closed form. So remember that I fixed the value of this guy, and all I need to do is compute the posterior of this. But the joint distribution of this is Gaussian. Because this is assumption. It's an assumption that for any finite dimensional observation, the joint distribution multiplied with Gaussian. So this is very easy for regression. For regression with noise, all you need to do is to be able to compute the posterior, which is your prediction at the test time, is to be able to do this inversion, and you have your condition, your posterior in a closed form in a very easy way. The problem becomes slightly more difficult when you have a likelihood that so that does not have a closed form, that does not look like a Gaussian. So an example of that is whenever you have, this shouldn't look like normal, but let's say that you have a y for classification that produces 0, 1 for you. If this is the 0, 1, then your likelihood is not going to look like a Gaussian because it depends on what kind of noise you have. So you cannot add a normal noise to this. So in this case, oops, your likelihood is not normal, but it has some sort of like a sigmoid function to this. You put your prediction function in, and that produces a chance of this coin flip, like 0 or 1. Because remember, your y is not Gaussian anymore. It's like 0, 1. It doesn't make sense to model it with Gaussian. The problem here is that when you have a likelihood that looks like this, you cannot absorb it with this your prior. So what should we do? At the end of the day, we are interested in computing this posterior of, this is this joint distribution of the training and the test data, which is proportional to your prior and the likelihood. But the problem here is that because your likelihood is not Gaussian anymore, you cannot absorb it back to your covariance function and use your short complement.
You can do gradient descent.
Well, gradient descent on what? So I'm not learning, right? I'm assuming that theta k and sigma are fixed, right? So there is no objective to learn, right? I'm interested in computing posterior. If you manage to write your inference as an optimization function, then you can use gradient descent. But first, you have to form your inference as an optimization function. What would happen if I somehow approximate this weird likelihood? I mean, it's not actually weird likelihood, but I can approximate it as a Gaussian, locally. What is the idea of, if I say I'm going to approximate something with Gaussian, what does it imply? The log of the Gaussian, if I take a log of the Gaussian, it's going to be quadratic function, right? So it means that the log of that function, I'm going to approximate it with the quadratic function. What does it bring to your mind? Taylor expansion, exactly. Taylor expansion of order 2, right? So let's take a log of this and do a Taylor expansion of the second order. Okay, so I went ahead of myself. So let's say that here I'm just showing you some examples. So let's say that I have some weird likelihood, which is like my, this is yellow graph here. I'm going to approximate it with the log of that with the quadratic function. So basically, I'm going to say that find a closest Gaussian distribution that looks like this. So what is the procedure for that? So the procedure for that is as follows. This is my px that can have any form, right? I'm not limiting that to any form. So I'm just saying that any density I can view it as exponential of some energy function with some normalizer. This can be applied to any density function. So far, nothing, I'm not assuming anything. But then remember that we are interested in approximating the log of this. So if I take a log of this, all I need to approximate is that I need to approximate this e function with the second order. So I'm going to find the peak, right? I'm going to find the peak and make a Taylor expansion around that peak. So around that peak is going to be constant, linear term, quadratic term. Right? This is just Taylor expansion. But because I found x star is the peak, and the peak is basically has a zero curvature, this is going to go away. It has a zero gradient, right? It's going to go away. And my Taylor expansion going to be basically this term, because this term, which is constant, is going to get absorbed in my normalizer. So all I need to do for any form of function that looks like this, I'm going to find their x star, and around that x star find the second order Hessian, which is h is the Hessian, and the inverse of the Hessian is going to be my covariance function. This method is called Laplace approach. Make sense? Why did I do that? Because what I did was that if this is my likelihood, I approximate this likelihood with a q that looks like normal. Now I can go back to my previous equation and replace this likelihood with q, which looks like normal, and absorb it back to this, and do my happy conditional estimation in the closed form. That's the idea of the Laplace approach. Make sense? The general idea behind this is that because Gaussian process, any finite evaluation looks like Gaussian, we have to hallucinate Gaussian out of this any likelihood form. So we are going to find a peak, make it look like Gaussian, and then do approximation. That's not the only way that we can do this, but it's quite an effective approach to do this. Make sense? Or should I, any part of that unclear? Yes?
Is there anything you need to do to make the Hessian a valid precision matrix?
Sorry, I didn't hear. What?
In the next slide,
Okay.
after you get the Hessian matrix.
Sorry. Hessian matrix, and what did I do?
Yes. Do you need to do something to make that a valid precision matrix?
Valid precision matrix. Oh, so you are worried that the result might not be positive definite?
But the inverse of the diagonal of the inverse, the H inverse is the diagonal.
If H is positive definite, H inverse is going to be positive definite. All you need to care about these functions is going to be just positive definiteness. So as long as I'm sure that H is positive definite, H is positive definite, my H inverse is going to be positive definite for sure, and then I'm good. So yes, if I have a function that H is not positive definite, then I'm in trouble. But I have to say, that's not the only way that we can do this. Laplace is like a simple approach that, because I introduced you that in a regression approach, if the noise is sigma square I can absorb it. For any other kind of likelihood, I want to make it look like Gaussian. And the Laplace is the simplest way to do this. But there are other approaches to do that. For example, the example that you just gave is that, remember, when we are interested in computing posterior, right? So we have seen in a few classes before, when you want to compute the posterior and posterior does not have a nice form, what is the approach that we usually take? Variational, right? You can view this as variational. You can assume a parametric form of variational and minimize the KL divergence or maximize the elbow. That's another way of doing it. Then you can cast it as optimization, you can do gradients. Make sense?
So in some sense, the Laplace method is only defined for likelihoods where the likelihood function is convex.
Log likelihood of that. The log of the likelihood is concave because that's a negative, right? Yes. But that is pretty big class. So what should we do for learning? So far I only talked about inference. I'm assuming that the parameters are fixed, but there are some. I want to do inference. What if I don't know the parameters? For example, a parameter that I don't know is like the width of the kernel, the nu of the matern kernel. So there might be some parameter in the kernel that I don't know. How can I learn those parameters? Well, the approach that we always take is maximum likelihood. So what we do here is that this is my input features, this is my prediction, and this is the function that produced that prediction. This is my, what is this? This is my prior, right? And this is my likelihood. If I integrate out the effect of f, I'm going to have a marginal likelihood that has some parameters hidden in it. That these parameters are parameters of, for example, kernel. Or can be parameter of the likelihood. So whatever parameters that you have here or here, it's going to be here. Right? You want to learn those parameters. So now the goal is that I want to maximize this log of the py given x. So again, we are going to fall back to our simplest case possible, which is the regression. So let's say for simplicity that my likelihood is simple normal distribution as it is in the regression case. You have already seen that if it is more complicated than that, for example, in classification, you can use Laplace approach to approximate it. But for now, for time being, let's assume that it's just a simple regression. So if this is the normal distribution, and this is the normal distribution, we know how to compute, because we know so much about the normal distribution, we can compute the marginal likelihood very easily. Remember that this is my prior that is coming from normal distribution. This is normal distribution. If I can put them together, my marginal likelihood is going to have a form that looks like this. I have ky that basically absorb the effect of my y. So it's basically my, oops. Okay, so my ky is basically k plus sigma I. Right? And this is basically the determinant of the ky, and this is a constant. If I want to optimize the parameters, whatever parameters I have in the kernel is going to show up here, and going to show up here. And I can do simple gradient descent to solve it. If I have other types of likelihood that I cannot write the ky that easily, I can use Laplace approach, make it look like Gaussian, absorb it to normal, here go, continue. So it seems that even the learning in Gaussian process is quite straightforward. So all you need to do is to take a gradient with respect to parameters, whatever parameters that you have. Usually parameters shows up in your kernel, and take a gradient. So the gradient of this term, because you can write this as a trace of ky inverse y transpose, is look like a linear term, like it goes out. And this is the log det of the kernel. The gradient of that is k inverse. That the forms are quite easy. Nowadays, you don't even need these because you just plug that into TensorFlow, take a gradient for you. But even the gradient of that is very simple. Compute. So what do you guys see as a challenge here in computing these gradients? It's easy to evaluate, but it's like, it has very simple form. But what would be the computational challenge? What is the computational cost to compute this gradient? Huh? N cubed, which is n if n is number of samples, is going to be n cubed y inverse. So what are the approach to avoid that? So it means that if you have a lot of samples, the naive approach is going to kill you because it's going to be very expensive every time you want to evaluate this gradient. So what are the approach that we can avoid it? Or reduce the cost?
You can assume that the kernel is just an outer product of two vectors. And so instead of using, let's say you want to use an RDF, instead of using the RDF kernel, you can represent by the features like.
So are you suggesting, for example, so let's dive into that. So this is expensive to compute, right? Because this is K inverse. One way of computing this is to limit the space of my function. So instead of having RBF, I can have space of linear function, and then I can probably approximate this easier. But that's going to limit this function, so it reduces my flexibility, right? Because I say that space of all of these nice smooth function, I'm going to be happy with the linear term. So that's one. But another way of viewing this is, if I have a K matrix, that my K matrix is low rank, right? I can write it as sigma sigma transpose. Do I still have to pay K inverse as O(n cube? Let's say that the rank of K is not n, is like less than n. Do I still need to pay n cube to invert it? What would be the cost? Let's say the rank of K is n, small n instead of capital. Some other numbers, this small. Huh?
Small n cube?
So it's going to be O(n square n). So one idea would be I can approximate K with a low rank matrix that approximately looks like K. If that approximation is easy to do, so I'm not deferring computation to something else which is as expensive, that I'll pay a lower cost. Another way of doing that is this, right? When you have something like A inverse something, some vector, you are interested in computing, you are basically solving a linear system that solves A x B. Do you agree? That's the same thing. So, but what do we do in reality when you want to solve this linear system? What do we do usually?
Use some iterative method like
Yes.
Jacobi or Gaussian.
Exactly, you can do conjugate gradients. So if you do conjugate gradient, usually if the so-called condition number of the matrix is good, you pay much lower cost. So you, instead of computing K inverse X, you can plug that. So because this is the step which is expensive, right? You can solve this with the conjugate gradient.
But gradient is still a matrix, right?
Gradient is matrix, yes. Well, no, the gradient is not a gradient is as because of dimensionality. Whatever the dimensionality theta is. But yeah, are you talking about the storage?
No, so it's K inverse of the
Something.
this, but then this is again a matrix, right?
No, it's
So it's a vector.
It's a trace out.
Oh,
Okay. So this is basically for computation. You can do low rank approximation, you can do conjugate gradient. Another thing that you have to circumvent is the storage. If you have the naive way of solving this is going to be, if K is n by n, the storage is going to be n squared. Right? That can be quite expensive. Because your K is n by n. You have to store all of its values. So one way to do that is to call a corset method, but I'm not going to go through that. So basically, you can keep some of the samples that are important and discard the rest.
So compared to neural networks that, like I think nowadays people, even for classification, they use neural nets. Nobody uses, I guess, for at least image classification, kernels. And I think statistically, there's nothing wrong with kernels. Like, what the problem is mainly probably the inverse. And I'm wondering, is there any way to catch up, or
What do you mean catch up?
to like have a performance that is?
Well, kernel ideas are still being used in neural network world. An example of that is you have already seen GAN, right? One of the successful cost function for GAN is MMD cost function. That MMD cost function under the hood is using ideas from kernel method. So yes, you are right. So right now we have moved away from the Gaussian process approximation of the function, and we have a space of, so we are basically explicitly modeling our features. That's basically what we are doing. But the general idea is still relevant because that shows up in a way that because at the end of the day, you have a neural network, you have to have a loss function, right? This loss function should come from somewhere. Either it's like classification, which is very simple type of approach. But when you are complicated things, for example, you want to approximate the density, then there is no simple loss function. And the successful loss function that we have, for example, MMD, are coming still from the Gaussian process world.
What I'm wondering is what do we need to do? Like, if we get computationally equipped to do these inverses, then basically we're done. Like we would.
No. I don't think that inversion is not an issue with the Gaussian process. I just told you that if you do the Gaussian process naively, you're going to pay the high price. So you have to do it in a more smart way by taking care of the storage and taking care of the inversion. That is not the reason. If you are comparing, for example, the performance of the Gaussian process with deep learning, that's not the reason that Gaussian process is falling behind.
But then what is it? Because we know that like on the large sample size, it should consistently estimate what it's supposed to do, right? If the
But what is large sample size? It's all asymptotics.
Oh, I thought you have finite sample guarantees for Gaussian processes.
What do you mean guarantee of what?
Like that your estimated parameters are close to the real parameters with a high probability.
Right, but if so we are still assuming, so it's something that we don't know. So something that we don't know, that the actual true function, it lives in our RKHS, right? We don't know that, right? We are saying that I'm hoping that my space of the function I'm searching with is rich enough that can include that true function. It may not include it. So it doesn't matter how well you approximate, there might be a big gap. Do you know what I'm saying?
Yeah, but is the class of functions that Gaussian processes represent is smaller than the class of function that neural nets represent?
I don't think we have we have quantitative answer to that. That this space is bigger than the other space. I don't think we can answer that. I don't have answer to that, at least. Okay, so we talked about that the choice of the kernel is important. So let me give you an example, practical example. So here is very famous data set. It's amount of CO2 emission from 1960s to the year 2000. And let's say that you want to predict the amount of CO2 emission in year 2020, let's say. Well, like if I show it to human being, what do we see? So we see that there's an increasing trend. Unless you're Donald Trump, you see that it's an increasing trend, and there's a fluctuation, perhaps because of the seasons. Well, so you do expect that in year 2020 you have more CO2 emission, and because this fluctuation is going on, you do expect that fluctuation going on. What would happen if, for example, I use RBF kernel to that? So I'm going to try some RBF kernel on this with two kernel. And you see that one of them expect that the amount of kernel emission drops suddenly after 2020, and the other one does not account for fluctuation. So in that sense, both are producing terrible prediction. One predicts gigantic variance, which is even, like, is saying that even prediction, it's predicting even negative CO2 emission, which I don't know what it means. And the other one, it ignores, just gets the trend right, but it's not good. So I'm showing you this to tell you that the choice of the kernel matters. I mean, you guys have already seen some examples. So let's add something to this. What would happen if I combine these two kernels? It gets a little bit better, but really still not getting the trend. So what would happen if I combine these spaces together? So the things that I see is that there is some sort of a nonlinear trend to this, maybe like a quadratic. So maybe I add all of this space of the quadratic function, and I see some, periodic function to this, and some other function that has to be taken care of. So if I combine multiple functions to each other, for example, a space of all quadratic, bunch of kernel function to each other to consider the smooth changes, and periodic function, you see that my prediction improves quite a bit. Because I'm searching a much bigger space. So I'm showing you this to say that the recipe to coming up with a good kernel is basically combining these different behaviors of the data. In fact, a couple of years ago, there was some paper that was saying that, well, maybe we can use some sort of like automatic statistician that like plays with different kernel, with different form of kernels and compute marginal likelihood, and plug in and out different kind of kernels to search within the space of all possible scenarios. How does it extend to the general graphical model? So here's the general idea. Remember the general graphical model. So I'm showing you a very simple case. So let's say they have 3 random variables, so A, B, and C. If they are discrete, what I'm modeling is this CPDs, this discrete distribution between every pair of the random variables. And if I'm doing something with continuous data, I'm sort of like go and directly parameterize the joint distribution. How can I extend it to the non-parametric case? So that's a general idea that when you want to extend this to the general Gaussian process, you want to get rid of this parametric form. Either if it's discrete in the table or into parametric form, you want to get rid of it. The key idea here is that we want to represent the distribution with this infinite dimensional object. Remember that the key reason for the success of the Gaussian process was going from explicit representation of the features to this high-dimensional representation of the features that we never work with directly. What if we can do the same thing for the distributions? So that was very smart idea by Arthur Gretton and Alex Smola, a few others. Sorry that I don't remember the name of all of the authors. So basically the idea was, well, why not going and instead of having parametric form, apply the same idea to the distributions. So let's say that this is my form of the data is coming from some distribution. It can be any crazy form, multimodal or anything. So what would be the key idea to represent these features? One idea would be, well, what if I compute the mean of the distribution? But the mean of the distribution is not enough. I can have, let's say that if I say the mean of the distribution is 0, I can have Gaussian with the mean 0, I can have Laplace with mean 0, I can have Cauchy with mean 0. Having mean is not enough. So what if I add more and more moment to this? So this is the first moment, I can add the second moment, third moment, an infinite amount of moments. Although that this is roughly the same idea, it's not very practical because how many moments? Then even if I have a lot of moments, I'm going to have like an infinite dimensional space. How am I going to do this? So the general idea here is that what if we just have this abstract object, this phi x, and we can somehow compute the not even our representation would be expectation of that. So think of this as a sufficient statistic. So if I have a feature space, this infinite dimensional feature space, my representation of the distribution would be expectation of that. So in interest of time, I'm not going to continue this, but basically the idea boils down to estimating that and representing the distribution like that. So next class would be our last class, and we'll go from there. Thank you.